this part, we're going to find the temperature of a body with a special formula. So guys, today we're going to look at another formula with the Celsius scale and the Kelvin scale and using other thermometers. Okay, so let's start with the Celsius scale. With the Celsius scale, you could be asked to find the temperature of a body using this formula. T is equal to X T minus X naught all over X at 100, X at 0, then times 100. This is degrees Celsius. Here are the parameters. This X we see here stands for the thermometric property. This means that this S could be used for any thermometer. So we look at the types of thermometers. That's the resistance and the resistance, whatever. Then this XT will be the thermometric property at temperature, at the temperature which we are measuring the body. And this X naught here, or X0, will be thermometric property at ice point. X100 or X at 100 is thermometric property at 100 degrees Celsius, which is the same as the steam point. T is the temperature of the body, and the unit of this T is degrees Celsius. The unit of the T is degrees Celsius. So guys, let's prove the formula. So assuming X, which is the thermometric property, is linearly proportional to temperature T, we're going to have a graph like this. So here will be X instead of Y axis, and the head here will be T instead of X axis. So this is what we're going to get. Here will be 0, and then our graph will be like this. The graph is not starting from this point at 0 because here is our X at 0, which could be any number above 0. And here will be our 100, which is the ice point. So if we trace to this line, then to this point, you will get X at 100. And then we have T, our T here. The same way we trace this to this point, to this side. So here will be X at T. So let's name this diagram as A here, and then B, and then C. So we're going to find the gradient at AB, which is equal to gradient at AC. So gradient at AB should be equal to gradient at AC. So this is what you're going to get. Gradient is change in Y over change in X. So gradient at AB here. The Y for the AB, which is from here to here, we get this. So we get X at 100 minus X at 0 divided by 100 minus 0, which is this, which is equal to gradient at AC. So we get X at T minus X at 0 divided by T minus 0. Yeah, so let's do some simple mathematics here. So here will be X at 100 minus X at 0 divided by 100 minus 0 is 100, which is equal to X at T minus X naught divided by T. Starting from this point, we're going to do some cross multiplication. We're going to multiply this T by this whole expression here. This 100 will multiply this whole expression. So we're going to get T multiplying X 100 minus X naught, which is equal to 100 multiplying XT minus X naught. So by making T the subject, you're going to get T, which is equal to XT minus X naught divided by X at 100 minus X naught, all multiplied by 100, and the unit is degrees Celsius. So mind you, X is the thermometric property that I said. So this whole thing is what we're going to write, same for the Kelvin scale, but it's just a matter of replacing the T here and the naught here and the 100 here by certain figures. So for the on the Kelvin scale, it will be, the temperature will be equal to x at T minus x at 0 divided by x at TR, which is the triple point minus x at 0. Then this will multiply 273.16 Kelvin. So let me show you one trick here. The trick here is that in some questions, the question will not mention any thermometric property at x at 0 or at the ice point or the absolute 0. When you are using the Kelvin scale, we call it the absolute 0. So the question will not make mention of that. So it means that that whole thing, x at the absolute 0 is equal to 0 as in figure. So it means that it will be T is equal to xt minus 0 divided by x at triple point minus 0 multiplying 273.16 Kelvin. So our new formula is equal to T is equal to x at T all over x at TR, which is multiplying 273.16 Kelvin. So our new formula is T is equal to xt divided by x at triple point multiplied by 273.16 Kelvin, when the question did not mention of x at absolute 0. Good. So we're going to look at how we will apply these two formulas with the types of thermometers. So we'll start the liquid in glass thermometer. This is not anything difficult. The liquid in glass thermometer, the mercury just read, or the alcohol read by a thread. So we said it's in length. So we just replace the thermometric property by L. So we just replace the thermometric property here by L. So here will be L at T, here will be L at 0, here will be L at 100, then here will be L at 0. Simple. The same thing for the Kelvin scale. Here will be L. That is the length of the thread or of the mercury thread. The same thing for constant volume gas thermometer. That one measures in pressure. So we say it is P. So just a matter of substituting by P. So here will be P at T. Here will be P at 0. Here will be P at 100. And then here will be P at 0. So the same thing for the Kelvin scale. Here will be P at temperature, P at absolute 0, P at triple point. Here will be P at absolute 0. Good. So let's move on to electric resistance thermometer. Electric resistance thermometer. This one, it measures the temperature in resistivity or in terms of resistivity. So we're going to substitute P by R in all the formulas. So here will be R, here will be R, here will be R, here will be R at 0. The same thing on the Kelvin, R at temperature, R at 0, R at triple point, R at absolute 0. And for the last one we're going to look at is the thermocouple thermometer. This one measures the temperature in terms of EMF, that is the electromotive force. So we're going to substitute by E. So here will be E at temperature, E at 0 or at ice point, E at 100 or steam point, E at ice point. Then here E at temperature, E at absolute 0, E at triple point, and then E at absolute 0. Don't forget, on the Kelvin scale, we multiply the whole thing by 273.16 Kelvin, and on the degree Celsius scale, we multiply the whole thing by 100 degrees Celsius. Let's take an example. So let's consider the question above. It reads, a resistance thermometer reads 21 ohms when placed in melting ice and 120 ohms when placed in steam. Determine the temperature of a hot liquid at which the thermometer reads 85 ohms. So by explanation, the question stated clearly that we are using the resistance thermometer in the sense that we are saying a resistance thermometer, so that is a keyword. So by explanation, the 21 ohms is the resistance of the thermometer at the melting ice, which is the same as the resistance at the 0 degrees Celsius, and the 120 ohms is the resistance of the thermometer at 100 degrees Celsius, which is the steam point. So we are supposed to determine the temperature of the hot liquid at which the thermometer is going to read 85 ohms. So our RT here, the R, which is subscript T, will be 85 ohms. So we are going to find the capital T from the formula that we just learned. So we're going to modify the formula, which was T is equal to X at T minus X at 0 divided by X at 100 minus X at 0 times 100 to T equal to R at T minus R at 0 divided by R at 100 minus R at 0, all multiplied by 100 degrees Celsius. So by substitution, we're going to get 85 minus 21 divided by 120 minus 21, all multiplied by 100 degrees Celsius, which is going to give us 64.64 degrees Celsius. So the same rule works for all the 4 types of the thermometers we learned, and it's the same principle that we use, and we use the same method for both the Celsius scale and then the Kelvin scale.